The $2 salt pipe versus the $180 billion energy industry. Who is hiding the truth? Imagine your electricity meter spinning quietly in the darkness, even when every light in your home is switched off. This isn't a malfunction or a haunted appliance. This is the silent drain of reactive power, an invisible force that costs you money every single month without delivering any useful energy to your household. Reactive power is electrical energy that flows back and forth between your home and the power grid, like an endless tide that accomplishes nothing productive. It powers the magnetic fields in motors and transformers, but never converts into light, heat, or motion. Think of it as the ghost in your electrical system, constantly moving but never working. Here lies the deception built into your electricity meter. Residential meters are designed to count every unit of electricity that enters your home, but they never subtract the power that flows back out. Industrial facilities with expensive metering systems can track this bidirectional flow, but your home meter operates on a one-way counting mechanism. You pay for the incoming surge, but you never get credit for the returning wave. The financial impact is staggering when calculated over time. The average household loses between $22 and $37 every month to this invisible drain. Over a 30-year mortgage period, a typical family wastes $11,700 on electricity they never actually used. This money vanishes into the revenue streams of utility companies, forming part of a $180 billion industry that thrives on consumer ignorance. The question becomes unavoidable. Where is this money really going? The answer reveals a hidden revenue model that has sustained the electrical utility industry for decades, built on a technical loophole that most homeowners will never discover. The suppressed pioneers. The story of reactive power suppression begins in Sweden during the winter of 1952. Dr. Lars Ericsson, a physicist working in a laboratory in Stockholm, made an accidental discovery that would threaten an entire industry. While conducting experiments on pH measurement systems, he noticed something peculiar. A glass tube filled with sodium chloride positioned near his electrical equipment was somehow reducing the reactive power readings on his instruments. Ericsson spent months verifying his observations, convinced he had stumbled upon a fundamental principle of electrical engineering that had been overlooked. In 1954, he published his findings in a Scandinavian technical journal, documenting how ionic crystalline structures could influence electromagnetic fields in AC circuits. The publication barely circulated beyond Nordic academic circles, and within years, the research disappeared from international discourse entirely. 15 years later, across the Atlantic Ocean, an electrical engineer named Gerald Morrison was conducting his own investigation in Arizona. Working independently and completely unaware of Ericsson's Swedish research, Morrison collected detailed electrical consumption data from 200 residential homes over an 18-month period. His conclusion was identical and alarming. Households could reduce their electricity bills by 23% using a simple passive device positioned near the main electrical feed. Morrison presented his findings to the Arizona Public Utility Commission in 1969, expecting recognition or at least further investigation. Instead, his research was classified as a threat to utility revenue stability. The commission quietly shelved the report, and Morrison was discouraged from publishing his work in any public forum. The data vanished into regulatory archives, inaccessible to the general public. That same year in Germany, engineer Hinrich Braun was conducting parallel experiments in 12 residential properties near Hamburg. His controlled study demonstrated an 18% reduction in monthly electrical consumption, using the exact same principle. Braun attempted to present his findings at an international electrical engineering conference, but his paper was rejected without explanation. The industrial establishment maintained its silence, and 3 independent discoveries on 3 continents were buried within the span of 17 years. The $180 billion industry greed. Large commercial facilities have been using reactive power correction technology for decades, yet this knowledge has been deliberately kept from residential consumers. Factories, shopping malls, and industrial complexes install power factor correction systems as standard practice because utility companies impose substantial penalties on businesses that draw excessive reactive power. These corporations understand that inefficient power consumption cuts into their profit margins, so they invest in correction equipment that can cost thousands of dollars but saves them millions annually. The Tennessee Valley Authority provides a revealing case study in this double standard. Commercial and industrial customers who improve their power factor receive direct credits on their monthly electricity bills. The utility openly acknowledges the value of power factor correction in their commercial rate structures, offering financial incentives for businesses that reduce reactive power consumption. Yet the same authority never discloses this information to residential customers, who collectively represent the largest segment of their revenue base. The mathematics of suppression become clear when projected across the residential market. If every household in America installed a simple reactive power reduction device, the utility industry would face an annual revenue loss of approximately $40 billion. This figure represents pure profit margin, money collected for electrical flow that performs no actual work. The industry has built entire business models around this technical inefficiency, creating a financial incentive to maintain consumer ignorance. Electricians and electrical contractors participate in this silence, whether consciously or through institutional training. A licensed electrician will charge $400 for a service call to diagnose phantom electrical drain, but will never mention a $2 solution that could eliminate the problem permanently. The trade associations that certify these professionals receive funding and sponsorship from utility companies and electrical equipment manufacturers, creating a web of financial relationships that discourages disruptive information from reaching consumers. This system of selective disclosure has persisted for over 5 decades, protected by technical complexity and the assumption that average homeowners lack the knowledge to question their electricity bills. The industry counts on consumer passivity, knowing that most people will never investigate the physics behind their monthly charges or discover that a simple solution has existed since 1952. The forbidden physics. The science behind this suppression lies in the molecular structure of sodium chloride, common table salt. At the atomic level, salt forms a crystalline lattice where sodium and chlorine ions arrange themselves in a precise geometric pattern. When exposed to ambient humidity in the air, these crystals develop a thin ionic layer on their surface, creating a unique electrical property that exists nowhere else in common household materials. This ionic layer responds to alternating electromagnetic fields in a phenomenon called ionic polarization. When an AC current flows through nearby electrical conductors, it generates an oscillating electromagnetic field. The ions in the salt crystal lattice react to this field by migrating microscopically back and forth within the crystal structure, following the alternating polarity of the field. This movement is not random. It follows the exact frequency of the AC current, which in most residential systems operates at 60 Hz. The migration of these ions creates what physicists call a displacement current. Unlike conventional electrical current that involves the flow of electrons through a conductor, displacement current represents a shift in charge distribution within a dielectric material. This displacement current generates its own electromagnetic field, and here lies the critical mechanism. The field produced by ionic displacement runs in opposition to the inductive reactive current flowing through your electrical system. The cancellation effect occurs through destructive interference. Inductive loads in your home, such as refrigerator motors and air conditioning compressors, create lagging reactive currents that oscillate out of phase with the voltage. The displacement current from the salt crystal generates a field that partially cancels this reactive component, reducing the total current measured by your electricity meter. The meter cannot distinguish between true power reduction and reactive power cancellation. It simply records less total current flow. The passive nature of this device represents its most elegant feature. Unlike capacitor banks used in industrial power factor correction, which must be wired directly into the electrical system and sized precisely to match the load, the salt pipe requires no electrical connection whatsoever. It operates purely through electromagnetic proximity, influencing the field around the conductor without ever touching the wiring. This makes it inherently safe and eliminates the risk of capacitor failure or harmonic distortion. A secondary benefit emerges from this reactive power reduction. Your electrical wiring operates at lower temperatures. When reactive current is reduced, the total RMS current decreases, which directly reduces resistive heating in the conductors. Lower operating temperatures mean reduced insulation degradation and decreased fire risk, extending the lifespan of your entire electrical system while simultaneously improving safety. The $2 revolution. The construction of this device requires nothing more than materials available at any hardware store, with a total cost that rarely exceeds $2. You will need a 1-inch diameter PVC pipe cut to a length of 6 inches, 2 PVC end caps that fit the pipe diameter, a small piece of fine mesh screen, and approximately half a pound of coarse salt. Pool salt works exceptionally well for this application because of its large crystal structure and lack of anti-caking additives found in table salt. The purity of the sodium chloride and the size of the individual crystals directly the effectiveness of the ionic layer formation. Begin construction by cutting your mesh screen into a circle slightly larger than the interior diameter of the PVC pipe. This mesh serves a critical function. It prevents the salt crystals from settling and compacting too densely, which would reduce the surface area exposed to ambient humidity. Push the mesh approximately 1 inch into the pipe from one end, creating a platform that will support the salt while allowing air circulation throughout the entire volume. Some builders use 2 layers of mesh, one at each end, creating a salt chamber with maximum exposure to air on all sides. The salt filling process requires attention to density. You want the salt packed firmly enough that crystals maintain contact with each other, creating continuous ionic pathways throughout the structure, but not so compressed that air cannot circulate between the grains. Fill the pipe slowly, tapping it gently against your work surface every inch of filling to settle the crystals without crushing them. The goal is to maximize surface area while maintaining structural integrity. Leave approximately half an inch of space at the top before sealing with the second end cap. Before approaching your electrical panel, understand that you are working near potentially lethal voltages. The main breaker in your electrical panel controls all power flowing into your home, and it must be switched to the off position before you open the panel cover. Even with the main breaker off, the incoming power lines from the utility remain energized, so never touch the wires on the utility side of the main breaker. Your work will be performed exclusively on the load side, meaning the wires that carry power from your breaker to your home circuits. Open your electrical panel cover and identify the main feed conductors that connect to your main breaker. These are typically the thickest wires in the panel, and in most residential installations, you will see 2 hot conductors, one neutral and one ground. The 2 hot conductors are where you will position your salt pipe. The device works through proximity effect, meaning it does not need to touch the conductors, but it must be positioned close enough for the electromagnetic field to interact with the ionic layer in the salt. The 1-inch rule represents the optimal distance discovered through decades of suppressed research. Position the salt pipe parallel to the main hot conductors, maintaining a consistent gap of approximately 1 inch along the entire 6-inch length of the pipe. Some installers use small plastic cable ties or non-conductive mounting clips to secure the pipe in position, ensuring it cannot shift or come into contact with any energized components. The pipe should run parallel to the conductors, not perpendicular, to maximize the length of electromagnetic field interaction. You may install 1 pipe near each hot conductor, or a single pipe positioned equidistant between both conductors. Field testing suggests that 2 pipes, 1 per conductor, provides marginally better results, but a single pipe still delivers substantial reactive power reduction. The device begins working immediately upon installation. There is no warm-up period, no activation process, and no maintenance required beyond the eventual replacement of the salt. The longevity of the salt depends entirely on your local humidity conditions. In dry climates, the salt may remain effective for 3 to 5 years because low humidity slows the dissolution of the crystal structure. In humid coastal regions, you may need to replace the salt every 2 years as moisture gradually dissolves the ionic layer and reduces effectiveness. You will know replacement is needed when your electricity bills gradually creep back toward their previous levels. Simply remove the end caps, dispose of the old salt, and refill with fresh, coarse salt using the same packing technique. Some advanced builders construct multiple units and position them near individual high-consumption circuits, such as the air conditioning system, electric water heater, or workshop circuits with heavy motor loads. This distributed approach targets reactive power at its source, potentially delivering even greater reductions than a single unit at the main panel. However, for the average homeowner, a single unit at the main feed provides the most dramatic and measurable impact with the least effort. The implications of widespread adoption extend far beyond individual household savings. If this knowledge spreads to even 10% of residential customers, utility companies will face quarterly revenue shortfalls that cannot be explained away as weather variations or economic downturns. The industry has maintained this monopoly on information for 55 years, built on the assumption that consumers would never question the technical complexity of their electrical systems or investigate alternatives to accepted practices. This is forbidden knowledge in the truest sense, not because it is illegal or dangerous, but because its dissemination threatens a revenue model that has enriched utility companies for generations. Every month that passes without this information reaching the public represents another $40 billion transferred from residential customers to corporate shareholders. The suppression continues only as long as silence is maintained. Share this information widely, document your results, and publish them where others can find them. The revolution begins not with legislation or regulatory reform, but with individual action multiplied across millions of households. Build the device, install it, measure the results, and tell everyone you know. The monopoly ends when enough people stop paying for electricity they never use.